So if you remember around the time of Newton, there were a bunch of different people who were trying to find out what the acceleration of gravity is. And so we had Galileo, who was dropping things off of the Leaning Tower of Pisa. We have Newton, who was trying to calculate it based off of his calculations. And there was a Frenchman by the name of Atwood who figured out that he could sort of trick gravity by counterbalancing two masses like this. So I want to show you in this sample problem how to do an Atwood machine problem. So if I have this mass over here, I have this mass over here. Remember, the first thing I'm going to do with any sets of forces is I'm going to draw a force diagram. So I'm going to imagine there be forces on this guy. I'm going to imagine there are forces on this guy. So the thing that's pulling this down is going to be the force of gravity. And the thing that's pulling up is going to be the tension in the string that is pulling on that. Over on the smaller mass, I'm going to have also a tension that is pulling up, and I'm going to have the force of gravity of this smaller mass pulling it down. So that'll be little m, this would be big M. Now, if I want to find the acceleration of that, so I'm looking for A, then I'm really looking at all of this together, which means that I'm essentially going to add up all the forces. Now, remember that a pulley, all it does is it's changing direction. So in essence, these two tensions, if I were to flatten this out, I could picture it as the one tension pulling this way. This would be the force of gravity of the little mass. And then over here, I'd have the other tension pulling this way, and this would be the force of gravity of the big mass. And so in essence, our two tensions are going to cancel out, and I'm left only with the two forces of gravity that are acting against each other. So I'm going to take then and say the force of gravity of the big M, because it's going to move that way since the big M has more mass, minus the force of gravity of the little m, and that's going to have to equal the total mass times the acceleration, total mass times acceleration. So if I plug in my values, then this is going to be big M times gravity minus little m times gravity equals the two masses together, big M times plus little m times A. Now, thinking through this, remember that Atwood was trying to find G, and so he would measure what this acceleration value was. He could take big M minus little m times G equals big M plus little m times A. He could divide both sides by this term in order to solve for what that gravity value is. Well, now that we know what gravity is, 9 out of 10 times we're not going to be solving for that gravity. We're actually going to be solving for the acceleration, just like it has in the problem here. So in order to get the acceleration, I'm going to say that A is equal to big M minus little m times G all over big M plus little m. And I can start plugging in values then for that. I can say, hey, I have a 150 minus 40 times 9.8 all over 150 plus 40, and that gives me an acceleration value of 5.67 meters per second squared. Now, remember, because both of these are connected by a string, both objects are going to accelerate at that 5.67 meters per second squared. And also think through the fact that because this is an acceleration, the next step in the problem could be to take this back to kinematics and say, hey, if it falls for X distance, how long does it take? Or if it falls in a certain amount of time, how fast is it going? Or if it has a final velocity of, and so we can pull in all of that kinematics information. Now, the second part of the problem then is to find the tension in the string. So notice that whenever we looked at everything together, our two tensions canceled out and we couldn't use any equation that had a tension in it. However, if we don't look at them if we don't look at them together, but we look at them individually, so let's say I'm looking at just big M here, I could say that the force of gravity of the big mass minus the tension is equal to the mass times acceleration of just the big mass. Vice versa, on the other side, I could take and say, well, this tension is pulling the little mass up, so I could say, or the tension on the other side minus the force of gravity on the little mass, has to equal the little mass times its acceleration. So if I go ahead and plug some numbers in here, I'm going to have, or some variables, I'm going to have big M times G minus T equals big M times A. Remember, I'm solving for the tension, so I could take the tension to the other side, bring the MA to the other side, and say M times G minus A is going to give us a value for that. So I can plug in the 150 I'm going to take the 9.8 minus the acceleration that we got above, 5.67, and that's going to give us a tension of 619.5 newtons. 619.5 newtons. Now I can also take and double check myself. I don't have to do it, but I could if I have time and I want to make sure that I'm right. I could take this tension and say minus little mg equals ma. Take this to the other side and say equals ma plus mg, which would be m times a plus g. And if I plug in my values for that, I take 40 times 9.8 plus 5.67. And when I multiply that out, I should also get 619.5 newtons. Because it's the same string, and as long as the string isn't catching, which we'll talk about later when we get into rotational motion, then it should have equal and opposite tensions. Now, the reason that we didn't end up with a negative in one of these is because we took care of our directions inside of our Newton's equation here when we said the sum of all the forces. So for this one, we said that this way had a positive direction, and for the one on the left, we said that this way down had a positive direction. Well, if we had maintained the same direction, then one of them would have come out negative and one would have come out positive. So that there gives you a beginning of how to do some of the Atwood problems. Remember that they are all broken into sort of the same steps. Do your total masses, so break up into all of the different forces that you have for the force diagram, then split them into the net force equals the sum of all the masses times A to solve for your A value, and then look at them individually in order to find the tensions. So pick one of them, whichever one's the easiest, set up the net force acting on that one object equals that one object's mass times its acceleration, which you found above, and that'll help you find the tension for that